Sure. Monday. Yeah. Yeah, I'll probably start reading it tomorrow. I haven't looked at them yet, but Monday I'll have back.
Okay. We're gonna.
Yes. Yeah. Mhm. All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, doing good. Okay. So I don't have the midterms yet. It's been kind of a hectic week. So I will have them for you guys by Monday. Okay. So tomorrow is going to be a little bit more open for me. So I plan to start grading tomorrow, and then I'll grade through Friday, and then by Monday I'll have the exams ready for you. All right. And so today we're starting something new. So we're starting our second to last set of lecture notes on higher order schemes. And so this is the second part of the project. And so for those of you who've already started working, you probably know that the second part of the project is to implement something called higher order scheme. So we'll go over that today. We'll kind of define what that means, why it's important, and how to incorporate this in your final project. Right, and so I think that's about it. Are there any final questions? Are there any questions I can answer before we get started for today? Okay. Oh, one more announcement. So there is a homework. There is one more homework for this class. So that's homework 6, and that's going to be based around the higher order schemes. And so just so that you guys have a little bit of practice with working with it, you're not just blindly applying it to the final project. I want to give you guys homework as well as, of course, homework solutions to help you out with that. So I'm still getting that ready, so that should be up for you guys by tomorrow. Okay, so let's go ahead and get started. Let's talk about higher order convection schemes. Okay. And so, of course, based on the title, you can see that we're talking about convection, right? And so if you recall our discussions about convection, both with finite difference and finite volumes, convection always has its challenges. It's always a lot more difficult to work with than just pure diffusion. Okay. And there's a lot of issues with convection. So just to kind of list a couple, one thing that we always have to worry about is stability. And another thing, when we're in 2D and 3D, we haven't really talked about this all that much, just because it hasn't really been relevant. But when you have convection in 2D and 3D, you kind of have an additional source of error known as artificial diffusion. All right, and so just to kind of jog your memory, artificial diffusion is something that occurs whenever our convection velocity is not aligned with the grid, okay? And so, usually if you think about our usual grid in 2D, whether it be finite differences or finite volumes, our grid goes in kind of vertical directions and horizontal directions, right? So it looks kind of like, just like a waffle. Our grid looks something like this. So perfectly vertical lines and perfectly horizontal lines, okay? What can happen is when the velocity is not aligned with the grid, and so let's say it kind of goes in a direction like that, this can add additional errors to our solution. Okay? Sometimes they're really small, sometimes they're not noticeable, but sometimes they can add a lot of error. Okay. And so the solution to this, or at least the solution, the only solution that we've thought of so far is to, we could theoretically rotate our grid. And so if we just rotate our grid so that it aligns with the velocity, that's one way to deal with that. But that's kind of an annoying way to do it. So it's not the perfect way, especially when you have situations like the final project where the velocity kind of changes in every, the velocity direction changes at every location, right? And so if you look at the project, we have kind of a swirling velocity field like this. Right? And so it doesn't really make a lot of sense to try to match our grid to that swirling velocity field, because really that would be kind of really hard. Okay. And so we want to have a way to deal with these kinds of issues, because they can be pretty big sometimes. Okay. And so the way that we're going to learn how to deal with these is to basically change the way that we discretize our convection terms. Because actually, the limitation that we have right now is that our convection terms are usually only first order accurate or second order accurate, right? Depending on which scheme that we use, right? I'm going to make the argument that if we increase the degree of accuracy of our convection terms, then a lot of these issues are going to go away. All right, so I'll show you what this looks like with finite differences first. So we'll finish up all the finite difference stuff today, and then we'll probably start the finite volume stuff, and we'll probably finish it up on Monday. Okay. Okay, so starting with finite differences, let's look at a typical convection term. So remember, our convection derivative is our first order derivative. And if we go just based on accuracy, so if you go for our most accurate scheme, we have this, right? So we have our usual, this is our central difference scheme. And what we know is that this term is second order accurate. Right? That means if we decrease the grid size by half, then our error will go down by a factor of 4 because of second order accuracy. Okay. Okay. But this is not the only scheme that exists, right? And so for discretizing this first order derivative, we of course have forward difference and backward difference, and so those are options as well. But those ones are only first order accurate, so they don't really give us any. We can actually go beyond that, so we can actually go higher orders of accuracy, and we can try using those and see if they improve our issues. All right, so the one that we're going to use, the one we're going to focus on, at least for this class, is a fourth order accurate central difference scheme. And so the fourth order accurate scheme looks like the following. So just like before, we have our first order derivative. So I'm using the term order to kind of refer to several different things, but this is our convection derivative here. Okay. And if we were to increase the order of accuracy, you know, it would look something like this. Right. So this guy right here is fourth order accurate. And you can kind of see why. So if you compare that to our usual central difference here, okay. Obviously, the first thing that you see is that it's a lot bigger. So there's a lot more terms involved in this expression here. Okay. And so with more terms comes a greater degree of accuracy. You know, those terms kind of introduce some new concepts that we haven't really used yet, right? And so not only do we have I plus 1, I minus 1 in this fourth order scheme, we have I plus 2 and I minus 2, okay? And so what these terms are farther away neighbors. So let me just show you kind of in 1D first. Okay. And so what we're usually accustomed to is that if we're looking at our central node here, phi I, okay, we're accustomed to using kind of the phi I plus 1, phi I minus 1, which is the immediate neighbors. Alessandro, I see your question. I'll address in a second. So normally we just use our immediate neighbors, I plus 1, I minus 1. Okay. But in using this fourth order scheme, we have to go even beyond that. So we have to go to our further away neighbors, I plus 2, I minus 2. Okay. So of course, this means that our algebraic equations are going to be longer. But I think more importantly, it's going to change how we code these up a bit. And so this is going to introduce some additional challenges that we'll go over next. Okay. Okay, Alessandro, so your question. So can you compensate with a smaller grid size with a higher degree of accuracy scheme to save on computation time and still get a stable solution? Yeah, no, it's a good question. And so, you know, one thing that's interesting about just computational mechanics in general, you know, ultimately what you want is you know, a scheme that's accurate enough, right? And so there are multiple ways to accomplish this. So, you know, one way, you know, which we've learned so far is just to simply take your grid and just make it make the grid sizing as small as possible. And then to basically, you know, reduce the error that way. This, of course, you know, changing the scheme is another way to accomplish that. But there's going to be some trade-offs, like you said. So it's going to increase the cost using the scheme. And of course, you can compensate that by making your grid size bigger, so you have a kind of smaller number of nodes overall, like you're saying. Okay. And so there are kind of pros and cons to kind of each approach. And so, you know, for the higher order accurate scheme, the one that we're covering today, you know, I would say kind of the pros for that are that it deals with a lot of the convection specific issues that you would still kind of see even with kind of our usual scheme. And so, whereas if you just refine the grid a lot, you know, maybe you're increasing the cost of your simulation significantly without that much benefit as well. There's a lot of kind of nuance to it, but kind of the thing that I want you guys to focus on for this is that, you know, we're applying this specifically to convection because there are a lot of convection specific issues that can show up. And in the end, if you just apply this to the convection terms, you know, yes, you're going to have to pay a little bit extra cost, but then that's going to be a lot more worth it than just simply making the grid size as small as it can. Yeah. Does that kind of make sense?
Yeah.
Your question is a very good one. It has a very complicated answer, one that's not easy to answer in kind of just a couple minutes. Okay. All right, so let's see how this is applied in an example, just so that you can kind of see it in action. Okay, and I'm going to jump straight to 2D because really, if you're in 1D, it's really not worth it to do a higher order scheme. So let's see what it looks like in 2D. Okay, and so of course we're doing this with finite differences, and so that, remember, we're kind of taking a break from finite volumes for a second. So let's look at the following equations. We have 10 partial phi partial x plus 75 partial phi partial y is equal to 3 partial squared phi partial x squared plus partial squared phi partial y squared. Okay. And we're going to solve it on the following domain. Okay. We have our usual square domain. So we have Dirichlet conditions all around, and so we're going to have phi is equal to 25 at every location here. Okay. All right, we'll have Lx and Ly is equal to 1. From our equation, we can see that our x velocity u is equal to 10. Our y velocity v is equal to 75. Diffusion constant k is equal to 3. Okay. All right, so what we want to do is we want to solve this using finite differences. But instead of what we usually do for our two convection derivatives, but for both partial phi partial x and partial phi partial y, we're going to use a fourth order scheme. Okay. For the diffusion derivatives, we're just going to use our usual scheme. So we're not going to do anything special for it. So for this example here, I'm going to show you the process of how to kind of derive our new algebraic equation using the higher order scheme. You're going to need that skill. And so, I'll kind of take an aside here. So, for this set of lecture notes, where we talk about this higher order scheme, I'm going to do it for all stable problems. And so these are going to be cases, or excuse me, not stable. These are going to be for all steady problems. So there's no time marching involved. Okay. One thing I'm kind of intentionally leaving out of these lecture notes is combining higher order schemes with time marching. And so that's something you guys are going to have to figure out for your projects. And so part of that is going to be, how do you take an equation like this, apply higher order schemes for the convection, and apply time marching, and then use that to obtain your equations. Okay. And so that's one thing that you're going to have to do for your projects. And it's one thing I'll help you out with. I'm not just going to toss you to the wolves, but I do want you guys to at least try with that derivation. Okay, so I'll show you how to derive it with the steady problem here, and then you just have to, for the project, apply time marching on top of that. All right. Any questions on just the setup for the problem here? Okay. All right. So let's go ahead and derive our algebraic equation. And when I mean algebraic equation, what I mean is for the interior nodes. In other words, we're going to derive our equation And we're going to assume that we have enough neighbors on every side. Okay, we'll do that first, and then we'll go over the special cases where we don't have enough neighbors. Okay? Okay, so I'm going to start with the generic equation. So we're going to start with u partial phi partial x plus v partial phi partial y is equal to partial squared phi partial x squared plus partial squared phi partial y squared. Okay, so that's exactly the equation that we have for this example. Okay. All right, questions. Would using a higher order scheme change how the Neumann boundary condition is defined? Yeah, that's a really good question too. So you know, for the purpose of our class, no. And so for the purpose of our class, the Neumann boundary condition you can implement in the same way. But if you wanted to be consistent, and so if you want to be consistent that our Neumann boundary condition would also be fourth order accurate, then you would change that as well. But for the purposes of this class, especially for the project, I kind of designed the project in a way where the Neumann boundary conditions don't make that much of an impact on the results. You can just use our usual techniques for the Neumann boundary condition. Yeah. Mm-hmm. Okay. All right, so you know, for the project, what you would have in addition to this is you would have partial phi partial t out in front here, right? So that's what you have for the project, but we don't have that here, so we're going to ignore it. Okay. So here is our differential equation, and so let's go ahead and do what we usually do in finite differences, where let's replace each derivative with a finite difference scheme. So let's start with the convection term. So we have u partial phi partial x, right? And so remember, we're going to use a fourth order scheme for this. And so we're going to say u multiplied by minus pi plus 2 comma j plus 8 pi plus 1 comma j minus 8 pi minus 1 comma j plus pi minus 2 comma j. Okay. All divided by 12 delta x. Okay. Plus v Okay, so we're going to do the same thing for v here, except we're going to put the plus 2s and plus 1s on the j instead of the I. We have minus bi j plus 2 plus 8 bi j plus 1 8 bi j minus 1 plus bi j minus 2 all divided by 12 delta 1. Right. So that's what it looks like with the higher order scheme. So you can see there's a lot here. There's a lot we're going to have to simplify, but we'll do that in the next step. Okay. All right, but let's go ahead and plug in for our diffusion terms because we need those ones as well. Okay. And so for the diffusion terms, we're not going to change a thing. So this is going to be just our usual diffusion derivatives. B I plus 1 comma j minus 2 phi I comma j plus pi minus 1 comma j all divided by delta x squared plus pi comma j plus 1 minus 2 phi I comma j plus pi j minus 1 all divided by delta y squared. Right. That's all the finite difference stuff. So now the rest is just algebra and simplifying. Okay. And so let's go ahead and group the like terms. So we're going to group the terms according to the fees. So we have a lot of fee terms here. And so in fact, we have 9 of them, right? So there's a lot of coefficients here to sort, but just going to do it one at a time. Okay. So let's go ahead and start from the top. And so we have the coefficient for phi I plus 2 comma j, right? And so that's going to be a minus u. Oh, and one thing I'm also going to assume is that we're going to assume delta x is equal to delta y. And I'm going to plug in delta for that. Okay, so we're basically assuming we have even grid spacing, same grid spacing in the x and y directions. All right, so we have minus u delta divided by 12. This is multiplied by pi plus 2 comma j, okay, plus 2/3 times u times delta minus k. And it's going to be for phi I plus 1 j plus minus 2/3 delta minus k ui minus 1 comma j plus we have a positive u delta divided by 12 pi minus 2 comma j plus delta divided by 12 pi comma j plus 2 plus 2/3 v delta minus k pi comma j minus 1 plus v delta divided by 12 phi I comma j minus 2. Okay. Oops, sorry, I missed a term here. So sorry about that. Let me see what the best way to do this is. Okay, so this term right here, the j minus 1 term. So this should be j plus 1. Sorry about that. So one small typo. All right, and so the real j minus 1 term is actually quite similar. Minus 2/3 v delta minus k pi j minus 1. And then finally, we have the I comma j term, which is just 4k. It's 4k b I comma j. And it's all equal to 0. All right, so if you're kind of following along, and then for the term that I circled, the reason I have it circled is because I made a typo initially when I was writing that term. And so it should be I comma j plus 1. So originally I had j minus 1. So that was kind of the correction that I had there. Okay. Besides that, there's nothing special about that. It's just kind of one of the other 9 terms that we have. All right, and so remember, the reason I like putting these equations in this form is that, when you have it in this form, that when you plug this into MATLAB, everything in parentheses here is going to be exactly the coefficients in our left-hand side matrix. Remember, that's kind of why I go through the trouble of writing in this form, so that, when you're writing your MATLAB code, it, basically each term in parentheses there becomes a line of code in the MATLAB. All right. Any questions on this here? Okay. All right, so this equation here is very long, but it's also at the same time, kind of more of the same as what we've applied, right? But there is one issue here, okay? One issue that we have kind of dealt with, but the issue is kind of more amplified, right? And so remember, this equation here assumes that we have enough neighbors on all sides of our node, right? So not only do we have immediate neighbors, we have an immediate neighbor to the north, south, east, and west, but we also have neighbors even beyond that. So we have our neighbors' neighbors as well. So let me draw kind of a grid here. Let me bound it. All right. And so I'm going to highlight a couple nodes in this grid right here, just to kind of show you, some of the issues that kind of occur. All right, so let's look at it. Let's look at this node first. Okay. So the node I've marked with the red dot. Okay. For this node, we don't have any issues applying our equation, because if you look at all the neighbors, right, we have two neighbors to the north. Okay, so this is like N1 and 2. Okay. We have two neighbors to the east, and so this is like E1, E2. We have two neighbors to the west, W2 or W1, W2. And we have two neighbors to the south, so S1, S2. Okay. So that node has no issues. Okay. Let's look at another node. So let's look at this node right here. Okay. All right, so I've drawn a node in kind of the top right of the domain. Okay. This node here is sitting right on the boundary, right? And so for these kind of nodes, right, we obviously don't have enough neighbors, and so we don't have enough neighbors to the north or the east, actually. But if our node is sitting right on the boundary, then we know we can just apply our boundary conditions. So that node also is not an issue, or, when I say not an issue, what I mean is that we don't have to change what we usually do. Okay. And so in this case, we have Dirichlet boundary conditions all around. And so for that node right there that's sitting on the boundary, we just apply our usual Dirichlet boundary condition. Okay. Okay. So those are two cases where, we're kind of good. So, for boundary nodes and I'll call them kind of deep interior nodes, we don't have any issues. Okay. Let's look at one more node. So let's look at this node right here. Okay. All right. So it's a node I've kind of drawn kind of near the bottom. And so technically this is an interior node, right? Because it's not sitting on the boundary. And so we can't apply a boundary condition here, okay? So normally for these kinds of nodes here, we apply our interior node equation, okay? We have one problem though. So if we count the neighbors, so if we go north, east, and west of this node right here, you can see here that we have enough neighbors. We have 2, okay? But if we go south, we only have 1 neighbor to the south, right? So we only just have S1. And because if we go beyond that, we end up off the domain. We're not able to, we're not able to get an equation for that. Okay. All right. And so the question is, what do we do with this kind of node? So, a node that's technically on the interior, but not interior enough to apply our higher order equation. Okay. So we can't apply a higher order equation. We can't apply boundary conditions because it's not on the boundary. Okay? And so the only option that this leaves us is to apply our usual kind of our old school interior node equations that's not higher order. So this was our equation that we use kind of good old central difference for. Okay. And so it's a little bit of a bummer. And so, I get asked this question all the time because, for a node like this, the only problematic direction is south. And so, people ask me every year, so, can we still apply the higher order scheme in the east and west direction? Okay. So, technically the answer is yes. But, you'll be able to get a result from that. But in my kind of personal opinion, if you're going to kind of play by those rules, it kind of makes the coding a lot more complicated than it has to be. You make it a lot more complicated and you don't really get a ton of benefit from it. And so, what you're going to end up with is that, if you're going to selectively apply the higher order scheme in certain directions, you're going to end up with a lot of if statements in your code that make it usually very difficult to read and very difficult to kind of parse. And again, you're not going to get that much benefit because you're not getting the higher order in both directions. Okay. And so my solution to this, or what I usually do, is to say that if we don't have enough neighbors, then we just default to our usual scheme. Okay, so we kind of have 2 cases. So if in the case where we have enough neighbors, we use a higher order scheme. If we don't have enough neighbors, we just use our normal scheme. Let me write down our normal scheme again here. And so it's been maybe about a month and a half since we covered this. And so I think it's worth it for a reminder. This is our usual scheme. Or I should call this, just to keep it consistent with the final project, this is our basic scheme. So this is our basic scheme with central difference. This is our basic scheme with central difference for convection. Thankfully, it's a lot shorter because we don't have as many neighbors to deal with. That's our old scheme. Okay, maybe placed in a different way. I think maybe a few weeks ago we kind of phrased it differently. But to kind of keep things consistent with our higher order scheme, I displayed it in this way. Okay. Okay. Any questions on this? All right. And so if we go back to our grid right here, so this right here, of course, is kind of a smaller version of the grid. But you can see here we're going to have kind of three possibilities. Okay. On the one hand, if we're on the boundaries, okay, so for our boundary nodes, we're going to apply our boundary conditions on these. I'm going to go ahead and highlight that in red, or actually make use of this highlighter. So for that kind of outermost ring right there, we're going to apply boundary conditions. So same as before. Set of nodes we have is kind of this inner ring right here. So kind of this inner ring right here, these are technically interior nodes, but we don't have enough neighbors for the higher order scheme. So for this ring, we're going to apply basic scheme. Finally, I'll use that color already. For all the interior nodes. Okay. This is not a great example just because it's a small grid, but normally there's a lot more of these kind of deep interior nodes. For these ones here, we apply our higher orders. So that's kind of the hierarchy that you should use for these. Okay. And so what I'm going to do next is I have a sample code for you. And so I have a code where this is all implemented for you. Okay. I would say, the higher order schemes kind of in practice, or at least the theory for it is not that difficult, or at least, or I should say is kind of not all that different from kind of what we've been doing throughout the class. It's really just, applying just a different scheme for the convection. I think where higher order schemes get difficult, and I think what people tend to struggle with is actually the code. And so getting this logic down, and so, the reason I kind of spent time here to highlight this, getting this logic down and kind of, pinpointing, where you are in the grid, whether you're the outermost ring, you're the inner ring, or if you're on the deep interior, okay? That's the part that tends to be challenging for people. And so, following the logic of the MATLAB code is kind of key for this part. And that's what you're going to apply in the final project as well. Okay, so let me go ahead and jump to the MATLAB code. Okay. And I should have downloaded this before class started. But I wanted to see how the Lakers were doing, so. Were you asked? Yes, I did the Title IX training, so you don't have to worry about that warning anymore. It's going to take a minute to boot up. So. Okay. All right. So this code. Oh, I should share my screen so the Zoom people can see what I'm seeing. Okay. So this code's available to you online. And so if you go to week 14, it is the first of the two codes. So I posted two codes here. I don't know if we're going to get to the second one today, just because, it's already 6:15. But I did want to go through the finite difference version of this code. All right, so this is the implementation of the code that, or the problem that we were just going over for the example. Okay. And so you can see here that we have a length of 1 in each direction. The number of nodes in each direction is 50. Okay, so we have all our usual stuff here. So we have the grids, we compute the grid spacing, and we have variables for the diffusion coefficient. I should say diffusion. Sometimes I say velocity or viscosity, because viscosity is diffusion for fluids. Okay. And we have the x velocity and the y velocity. Okay. Okay, so let's get on to the kind of the what I wanted to kind of show off for this code, which is the logic. Okay. And so the most important thing when you're applying higher order schemes is to make sure that you have enough neighbors. Right? I think the thing that can be frustrating for people when applying higher order schemes is that you may get a lot of errors from the MATLAB, because you'll try to apply the higher order scheme, and then MATLAB will give you an error called index out of bounds or something like that. Okay. So you want to make sure your logic is sound for this. Okay. All right, so let's go ahead and jump into the loop. And so, just like we normally do for 2D problems, we have a nested for loop. And so we have a loop over I, J. Okay, so we're visiting all of the interior nodes. Okay. Next thing we're going to do is we're going to obtain all of the relevant ID numbers. And so this part is usual here. So this is present for all of our 2D problems. And so we have the ID number for I comma j. We have the one for the left ID, that's I minus 1, right ID, I plus 1, the up ID, and the down ID, so j plus 1, j minus 1. Okay. So these are all the immediate neighbors. So these are all of the neighbors that we usually use for 2D problems. Okay. What's new here is that, because we're using a higher order scheme, we also need the neighbors that are further away. So we need the I minus 2 neighbor, the I plus 2 neighbor, the j plus 2 neighbor, and the j minus 2. Okay. So that's what these 4 lines of code are. Okay. You can see here that they are very similar to their immediate neighbors, except I adjusted them based on because they're I plus 2, I minus 2. So they're a little bit further away. Okay. Okay. All right, and so from here, what I've done is I've kind of split up the contributions from the diffusion and the convection, because the convection is going to get a little bit complicated because we have the higher order stuff. But at least we know that the diffusion part is going to stay the same. And so the diffusion I've implemented in kind of the same way. Okay. And so for I comma j, the central node, we have a plus 4k here. Okay. And then for all of the immediate neighbors, the left neighbor, the right neighbor, the up neighbor, and the down neighbors, these are all the plus 1 neighbors. Okay. We have minus k for all of these terms here. Okay. And that's read just kind of directly off our equation. Whether we're using the higher order scheme or the basic scheme, the diffusion is going to stay the same. So that's why I've kind of done it separately. And then we're going to do the convection part, on its own. Okay. Okay. So before I get to the convection part of the code, are there any questions on kind of how the code is structured so far? Okay. All right, so let's get to the convection parts. Okay, so we can see here I've done the x and the y direction separately. Whoops. Okay. And so we're going to check in the x direction whether we have enough neighbors, and then we're going to check in the y direction whether we have enough neighbors as well. Okay. So for the x direction, so what we are basically checking for here is if we are on that inner ring. Okay. Okay. And so if we're on that inner ring, then what that is that, that's going to be when I is equal to 2, or if I is equal to n x minus 1. Okay. So let me kind of pause here for a second. And so when I is equal to 2, or I should say when I is equal to 1, okay. When I is equal to 1, that means we're on the very left edge of the domain. Which is essentially where we're going to apply our boundary conditions, right? And so if we go one column to the right of this, and so if we go to I is equal to 1, or I is equal to 2, okay, this is the inner ring. So this is the case where we have, not enough neighbors to apply our higher order scheme. So in this case, if we're on that inner ring, at least on the left side, we don't have enough neighbors to the left. is equal to 2, that means we only have one neighbor to the left. Okay. And so in that case, we have to apply our basic scheme. Okay, so that's why we have an if I is equal to 2 here. And you can see here that these are our usual kind of central difference schemes here. Okay. The other case where we apply our basic scheme is if we're on the right side. Okay. And so let's go through the same logic. And so when I is equal to nx, that means we're on the very, very right side of the domain. Okay. Which is where we apply boundary conditions. One step on the interior for this is I equal to nx minus 1. And so in this case, when I is equal to nx minus 1, we don't have enough neighbors on the right side. And so if we only have one neighbor on the right side, that means, again, we can't apply our higher order scheme. And so we have to go back to our basic scheme. Okay. So those are the two main conditions where we apply our basic scheme. So where we only have one neighbor on the left and we only have one neighbor on the right. And that is basically what these two conditions are telling us. Okay. Okay, and so if we're in either of these locations in the grid, then we're going to apply the basic scheme in the x direction. Okay? Otherwise, we're going to apply our higher order scheme. And so these are the 4 coefficients for the higher order scheme. So we have I minus 1, I minus 2, I plus 1, I plus 2. Okay. Okay. Any questions on this? I think I might have misspoke earlier, so I was kind of misremembering something just from lack of sleep. And so, you can see here that, we have separate if statements for the I and J directions. So that means that, because these if statements are separate, it is technically possible to have the higher order scheme in left and right, but the basic scheme in the other direction, north and south. Okay. I think what I meant to say earlier was that, if you don't have enough neighbors in the right direction, then we still apply the higher order scheme in the left direction. I think that's kind of what that's kind of what I had in the notes, and then my mind just kind of jumbled it. And so with this code structure here, it is technically possible that you have, right? So here is, maybe phi I comma j right here. Right? So maybe we have a higher order scheme in this direction. Okay? So we have enough neighbors. We have 2 neighbors to the left, 2 neighbors to the right. Okay? But if we only have 1 neighbor to the south, then we apply our basic scheme in this direction. Okay. So that's okay. And so, that's fine. We can have higher order scheme going east to west, but basic scheme going north to south, and vice versa as well. Okay. But what you can't have, or what is, I should say, a lot more difficult to implement, is that if you have, let's say that we only have 1 neighbor to the right, okay? We can't apply basic scheme in this direction to the right, and then apply a higher order scheme to the left. So that is a lot more difficult to implement, but north-south versus east-west, that's fine. Okay. All right, so I was just kind of clarifying just kind of something I said earlier. Okay, and so then we have the same thing in the y direction. So I'm not going to go through this in that much carefully, but the logic here is the same. Okay, and so when j is equal to 2. We only have 1 neighbor to the north. When we have 1 neighbor up top, that means we can't apply our scheme. Okay. Oh, I'm sorry. When j is equal to 2, we only have 1 neighbor below them. I need to get more sleep. Okay, so when j is equal to 2, we only have 1 neighbor below, but same thing. And so if we only have 1 neighbor below, we can't apply our higher order scheme. When j is equal to ny minus 1, we only have 1 neighbor up top. Okay. And so same thing, we can't apply our higher order scheme if we only have 1 neighbor in that direction. Okay. And so that's what this if statement is saying here. So if we only have 1 neighbor below or only 1 neighbor above, let's default to our basic scheme. Okay, so this is our basic central difference. Otherwise, then we can apply our higher order scheme, which is this guy right here. Okay. Okay. And then after that is just boundary conditions. So those are all pretty standard. So I'm not going to go over that again. Okay. And so let me go ahead and run this code just so you can see it work. Okay. And so here is our solution. And so in this particular problem, we have pretty strong convection. And so I think we had a convection velocity of 75 in the y direction, I believe it was. Yeah, 75 in the y direction. Excuse me. We have a convection velocity of 75 in the y direction. So that's why you see the solutions all kind of smushed in the vertical direction. And then in the x direction, we had a convection velocity of 10. So that's why it's kind of pushed over to the left. Okay. Any questions on this code here? Okay. All right, but that's kind of the basic logic that you would have to follow. And so, definitely use this code as reference. It's not exactly what you would use for the final project, because remember, the final project is using time marching, but you are going to have these if statements in your final project code for the finite difference. Okay. So definitely take the time. To kind of understand this, to kind of make sure you know kind of everything that's going on in terms of the logic, right? Rewatch this lecture if you have to, and then apply that to your final project. Okay. All right, so that is a higher order scheme with finite difference. Okay. Of course, there is a higher order scheme for finite volumes as well. So we're going to start talking about that today. We're not going to have enough time to finish talking about it, but then we'll resume it on Monday. Okay. Okay. And so just like the finite difference case, we're going to focus primarily on 2D. Okay, so I'm not gonna spend time with the 1D stuff. We're going to jump straight to 2D. Okay. And so for 2D finite volumes, remember the focus of our efforts are on the 4 edge integrals or 4 face integrals. We have one for the north side of the cell, one for the south side of the cell, one in the east, and one on the west. Let me show one here just for demonstration's sake. And so, for instance, on the east side of the cell, we have the following expression. And so we have integral of phi times v dot n minus k gradient of phi dot n. Okay. And when we apply our integration techniques to this, when we apply our trapezoidal rule mostly, okay, what we end up with is the following. So we have phi subfield e multiplied by u minus k partial phi. All right, so just like we did with finite differences, we're not going to focus on the diffusion term. So this term here is our diffusion term because it has k. So this is going to be the same. So I'm not going to, we're not going to go over that just because it's the same. We're going to focus primarily on this term right here, which is our convection. Okay? In particular, I'm going to focus on this term right here, this phi sub e. Okay? Remember, this phi sub e This phi sub e here represents the value of phi, or value of our solution, at the east face of our cell. So if I were to draw, let me go ahead and draw a picture for you. Let's say we have two adjacent cells here. And so remember, when we solve finite volumes, we're solving for the solution at the centroids of the cell. Okay. So for two adjacent cells, we have phi sub c and phi sub big E. Okay. This phi sub little e right here, remember, this represents the value of the solution right in between those two cells. Okay, so this right here is phi sub little e. Okay. And so what we usually do, and what we've done up to this point, is we use a central averaging between those two cells. What we said was that phi little e is equal to phi sub big C plus phi sub big E divided by 2. And so we did that, and then for the diffusion term, we did our usual kind of forward difference, and then we kind of combined it with the other integrals, and then off and away we. Okay. All right, but of course, this lecture here is about the higher order schemes, and so the question is, how do we make this higher order? Okay. So is there a way for us to make this higher order? Okay. And so if we take inspiration from our finite difference counterpart, and so if you kind of look back from earlier today, we saw how we made finite difference higher order. One of the biggest differences that we made was that we incorporated more neighbor nodes. So let's try that here too. So let's see what happens when we apply more neighbors. Okay. All right. So that sounds good in theory, right? So bringing more neighbors into the fray sounds good. But how do we actually do that? Okay. So we're not going to get into the derivation of this, but there is a scheme for this, and so people have thought about this already. And it actually has a neat nickname. Okay. So the scheme that we're going to use is called the quick scheme. Okay, where every letter in quick is capitalized because it's an acronym. Okay. Right. I'm going to show you the scheme, and then everyone will be thinking the exact same thing. Everyone will be saying there ain't nothing quick about this scheme. In fact, it should be called the slow scheme because it takes so much work to do. But quick is actually an acronym for something. Okay? And so if you're curious, you don't really need to know what it stands for, but in case you're curious, quick stands for this SpongeBob style where we have the letters all vertical like this. Okay? So So quick stands for quadratic. U stands for upwinding. I stands for interpolation. And of course, like every acronym, there's a forgotten word. And so there's a word called for here. Okay. So quadratic upwinding interpolation for convective kinematics. So quick quadratic upwinding interpolation for convective kinematics. Okay. If you've ever watched old episodes of SpongeBob, my wife recently rediscovered the episode where SpongeBob and Mike hang out together and they sing the fun song, the FUN song. And so she's been singing that a lot lately. So, you know, and if you watch the episode, they have this. I'm not going to sing. Okay, so here's how it works. And so the quick scheme has two versions. So the whole idea behind the quick scheme is to incorporate more neighbors, you know, for this convective term in a way that's kind of consistent and accurate and gives us kind of the best results. Okay. The reason we have two forms is that, you know, unlike the finite difference where we incorporate two extra neighbors, right? And so we incorporate kind of an extra neighbor on the left and the right, okay, or on above and the bottom. The quick scheme actually only incorporates one more neighbor. That makes it seem better, right? And so, you know, instead of adding two extra terms to our, adding two extra terms to our expression, you know, adding only one sounds good, right? But then if you're only adding one neighbor, the question then becomes, you know, do you add the neighbor to the left or do you add it to the right? Okay. All right, so let me show you kind of the two the two versions. And so for all of these, we're going to use the same figure. So let me go ahead and draw it. And so the cell in question is going to be this one right here. Okay. So this is phi sub c. So it's kind of in the middle, but off to the left. We also have the east neighbor. So this is phi sub big E. Okay. And we also have the neighbor that's two away. So we have phi sub 2, I'll call it phi sub 2e. Okay. But we're also going to have the west neighbor as well. So phi sub w, phi sub big W. So I'm going to do this example with the east face, but you know, the same kind of logic applies. Okay, so you know, it's just kind of easier just to show you just for one of the cases. Okay, and so for all these cases, we're trying to come up with an estimate for phi sub little e, which is where the red dot is. Okay. Okay. All right, so let me show you the two versions of the quick scheme. Okay. And so the first version, we're actually going to add the neighbor to the left. Okay. So this is going to be, we're going to add the neighbor on, I'll call it the opposite side. So the opposite side of where the face value is. And so since our face value here is on the right, that means we're going to add our neighbor, our extra neighbor to the left. Okay. And so in these cases, we have phi sub little e is equal to minus 1/8 sub big W plus 3/4 phi sub c plus 3/8 phi sub big E. You can see here that, we have phi sub c and phi sub e. So those two are going to be present always. But then the third neighbor that we added was on the opposite side. That's phi sub w. Okay. And so if we add the neighbors on the same side, we end up with the following. So phi sub little e. And so now we're going to incorporate phi sub 2e. Okay. We have minus 1/8 phi sub 2e plus 3/4 phi sub e plus 3/8 phi sub c. So you can see that the coefficient values are the same. So in both versions, we have a minus 1/8, we have a positive 3/4, and we have a positive 3/8, right? So those values stay the same. It's just that which phi values or which neighbors that we put them on depends on where we're adding the extra neighbor. Okay. All right. Any questions on this? Okay. All right. And so, the next question is, that you may be asking. So, we have these two versions, and hopefully it kind of makes sense about how we kind of chose these. And so the next question is, how do we choose which one to use, right? So, when we're coding, we obviously have to pick one, so we can't use both in our code. The next question is, how do we pick? Okay. So let me go back up to the acronym for quick, just really quick. All right, and so let's look at the second letter for quick, which is upwinding. Okay. So the second letter for quick is upwinding, right? And so upwinding is something that we've talked about before in this class, right? And so if you remember upwinding from when we did convection with finite differences, basically the idea with upwinding is that we applied more weight on the upstream side of the convection velocity. And so we're going to use that same logic here. And so the version that we pick is going to depend on the direction of the velocity. Excuse me. Right. And so the idea with quick is that, where we put the extra neighbor, whether we put it on the same side or we put it on the opposite side, we want that neighbor to be on the upstream side of the velocity. Okay. And so for this particular one, and we'll end with this today. Okay. Let's say the velocity is going from left to right. Okay. And so if the velocity is going from left to right, that means our velocity is greater than 0. So use greater than 0. Okay. And so if the velocity is going from left to right, we want to put more emphasis or more weight on the left side, right? And so that means we should use the first version. And so this first version, where we put more weight on the opposite side, is we basically add phi sub w into our expression. Okay? We're going to do that for the case when u is greater than 0. Whereas the other case is when u is less than 0. Okay? In other words, velocity is going from right to left. In that case, we want to put more emphasis or more weight on the right. Okay? And so for that, we're going to use version 2. Okay? So if you use greater than 0, you're going to use the first version. If you use less than 0, we're going to use second version. Okay. And we're going to apply that same logic to all 4 integrals. So we've done this for the east integral, and then when we come back on Monday, I'll show you kind of all expressions for all 4 of the integrals. It's going to be a lot of writing, but you know, it'll be good. All right, any final questions on this before we wrap it up for today? Okay, all right, so I'll see you guys on Monday. So I hope you guys have a good weekend. So thank you guys for coming today. I'll have your midterms ready on Monday as well. So so if you want to come by in person, pick them up, you can do that. Okay. So hope everyone has a good weekend, and I will see you on Monday. Been stuck in my head all day too. See you, Dominic. Have a good weekend. I grew up with SpongeBob. I used to be able to like memorize like certain episodes of SpongeBob. Like me and my sister, we would just kind of just say them. Now I can't do that anymore, but it's still a big part of my childhood. Oh, really? Nice, nice. All right, Abraham. Oh.